Hi, we're Anna and Jay. Our project is on pupil tracking and mouse behavioral study. Pupil tracking is a critical part of neuroscience to understand animals' behavioral state. We can know whether the animal is attentive, sleeping, or aroused using this. Conventional machine learning techniques fail to accurately detect the pupil in many cases. For example, when we have sleeping or cringing animal, or have light reflection patches or whiskers get in the way, machine fails to detect the pupil correctly. We aim to develop a pupil tracker that is easy to use and works on minimal computational resources. Many neuroscientists do not have expensive GPUs, so we developed pupil tracker that runs on a CPU and does not need any labeled data. We also compared our pupil tracker with other CNN-based image segmentation tools.
Detectron 2 is the most popular image detection algorithms available, and it is developed by a Facebook AI research team based on fast region-based CNNs and resonance.
So Deep Lab Cut is made from EPFL, and they're designed for 2D and 3D markerless pose estimator based on transfer learning with a deep neural network. To make our model, we first chose 200 frames pulled from 10 datasets, and we hand labeled 4 markers surrounding the pupil on all 200 frames. The labeled data is trained on a DNN consisting of resonance and deconvolutional layers, and once it trains for a few days, for 150,000 iterations on a CPU, the trained model can be used to predict labels on other mice pupil videos as seen in Figure D.
This is an algorithm for pupil tracker, and I highly recommend you to pause the video and take a look at it. First, we scoped down the tracking area only to the eye region to make it faster and to have only 2 colors, white and black. Then we scaled the window pixel values and binarized the image to get a threshold to differentiate between the pupil and non-pupil area. When it is done correctly, it accurately segments the pupil. As said in B, the threshold often fails when there is a light reflection or whisker in the way. Where we have accurate threshold value to segment the pupil, we provide the visualization to the user to determine whether the value is acceptable. In cases where we have impediments, offsets are added to compensate for these issues and then use our resulting k-nearest neighbor algorithm to create an elliptical mask for the pupil. As a result, our algorithm enables tracking and segmentation of the pupil through the video as seen in C. Our final output also gives functional values used to create plots like D.
So these are our results. Detectron 2 and Deep Lab Cut are CNN-based models. Both take training times of 4 days and have prediction times that are much longer than Pupil Tracker, which is our algorithm based on k-nearest neighbors. The good thing of a Pupil Tracker is we don't need to label data. It's easy to use, faster, and runs on CPU. That would help most of the neuroscientists. Thank you for listening.